Okay, working energy. So we're going to get through this quick where I don't go over my time limit again because, yeah, I don't really want to make you sit here and watch more than 15 minutes of me at once. Anyways, don't forget, Mr. Jones coming in tomorrow, observing. Make sure you understand this. Make sure you're ready for the video quiz tomorrow on concepts. And then we'll practice the math. So first thing, remember, force. Net force is applied in a direction, so it's a vector quantity. Net force changes the motion of an object. So it's going to change the velocity, or it's going to change the direction. It's going to change something with the motion. Now, energy. It's defined as the ability or capacity to do work. So if an object has energy, it can do work. It's going to do something. Energy is measured in joules. So that's our unit. Joules of energy, abbreviated as a capital J. Now, there's two main kinds of energy. There's kinetic energy, there's potential energy. The first one we're going to deal with is kinetic energy. We're going to deal with kinetic energy first because it's the simpler type of energy, because there's only one type of kinetic energy. It's derived from the motion of an object. So there's two things we have to look at to figure out kinetic energy. We have to look at the mass of an object, and we have to look at the velocity of an object. The bigger the mass, the greater the energy. The higher the velocity, the greater the energy. Velocity having the greater impact on energy. The more a change in velocity has a greater change for energy than a change in mass. If you look at the equation, you can kind of see why. Because when we look down here, the m is just single time, the v is squared. So if we square v, a little change here is going to carry out a bigger change overall. So let's go ahead and look at an example of this. So my example is 5 kilogram ball that is traveling at a rate of 5.7 meters per second squared. So this is just finding kinetic energy. It's really straightforward. So we're going to find Ke. So we have 1/2, so 1/2 times m, which is our mass, which is 5 kilograms, times v squared, so 5.7 squared. Be very careful, order of operations here. You want just the 5.7 to be squared, not everything, which gives us a kinetic energy of 32.5 joules. So with all this information, we're going to have 32.5 joules of energy. If we increase the mass, we're going to have more energy. If we increase the velocity, we're going to have more energy. Now, if we're applying a force to this, which one are we going to change? If we're just applying a force, we're going to change the velocity. We cannot change mass by changing force. We'd have to add mass to this to change it, because remember, conservation of matter cannot create or destroy matter, yada yada yada. That should be kind of review from chemistry. Anyways, potential energy. It's derived from the stored energy. So this is energy that is not actively doing something at the moment, but it has the potential to do something. There are three main ways of storing energy when you break it down to the simplest forms. There's chemical energy, which is stored energy in bonds. That's the type of energy our body uses. When we eat food, we get in the chemical energy, and our body converts it into whatever energy we're going to actually need. The two main ones we deal with in physics are elastic and gravitational. Elastic energy is stored by deforming an elastic material. Any object can hold elastic energy, it's just how well it does. An elastic material is a material that easily can be stretched out or deformed and returned to its original shape. So not everything is as elastic as everything else. Then when you look at gravitational, this is stored by changing how far from the center of gravity you are. So the farther away you are from the center of gravity, the greater your gravitational potential energy, because there's a farther distance you can fall. It's that simple. We're going to start with elastic potential because this is the one that's kind of really straightforward, simple, quick, get it done. It can be calculated for several materials based on what the materials are. The biggest thing you're usually going to have to figure out is what is your K value, because any different material, any different size spring, anything has a different K value. Usually your K values have to be experimentally determined before you can do anything else. Now, one of the reasons we tend to stick to springs versus, say, rubber bands or anything else is because springs do not tend to fatigue as much as other materials. The fatigue is where the material weakens over time, which means the energy stored changes, because each time we stretch it out or compress it, it becomes weaker. Springs tend to hold their shape better, so we can use a spring more before it starts to fatigue or weaken. Now, to calculate our potential energy stored in a spring, we use the 1/2 kx squared. The K is the spring constant. Again, this is usually found through experimental data. If you're having to solve a problem having to do with spring potential energy, I'm usually going to give you the K value. Even the state is usually going to give you the K value. There is no set K value for all springs. You're going to have to find it each individual time, usually in the problem. The X is the distance the spring is deformed. So it's not, hey, my spring is this long, it's how far we stretched it. So if we have a spring here and we stretch it to here, it's not this distance, it's the difference between the two. Many times you're going to be given the distance, this is how far we deformed it, not this is how long the spring is. But you should be able to figure it out. So let's look at an example here. What is the potential energy stored in a spring that has a spring constant of 273 newtons per meter and is deformed by 0.105 meters? So our equation, 1/2 kx squared. So we're going to do 1/2 times k, which is 273 newtons per meter, times our x, which is 0.105 meters, 0.105 squared. We cannot forget that square. We always have to remember it, which gives us 1.5 joules of energy. So that spring has only stored 1.5 joules of energy. So that spring can now do 1.5 joules of work to something because it has 1.5 joules of energy. Now, other type is gravitational potential energy. This is all based on how far you are from the surface of the Earth, or how far from the surface of Earth you are, either way. So this one, again, we usually stick to planet Earth because we can remember 9.8 meters per second squared is lowercase g, the acceleration due to gravity. If you're not on planet Earth, I'm going to tell you. And normally for this, we're going to assume we're close enough to the surface. We don't have to worry about the changes in gravity due to the law of universal gravitation. I'm not that evil. So to calculate potential energy,
Missy, please call 100. Missy, please call 100.
it's just mass times gravity times height. So let's look at an example. What is the potential energy of a 500 kilogram car that is at the top of a hill that is 25 meters high? And yes, I still have a typo there. So 500 times g, because it's mgh, which is 9.8 meters per second squared, times 25 meters, gives me a potential energy of 122,500 joules. So that car, once it's at the top of that 25 meter high hill, has 122,500 joules of potential energy. So it could possibly do 122,500 joules of work. Work is defined as the amount of energy changed by the application of force over a distance. So when we do work, we're applying a force over a given distance, and then we're changing the energy of something. It too is measured in joules. Pretty straightforward. Now, the easiest way to usually calculate work is if you have, this is how much energy I had before I did something, this is how much energy I had after. And we just find the difference because the energy had to go somewhere. So our work was how much the energy changed. Because if I lost energy, something had to gain it. If something else gained energy, I had to lose it. I get the point. If we don't have two energies, we can also just look at it's a force applied over a distance. So, yeah. And when we apply the force, we have to change the motion, or we have to somehow deform something or lift it up. Otherwise, it's not really going to change the energy. So if I apply force pushing someone, they're going to move faster. If I apply force to a spring to squeeze it down, I'm compressing it. If I'm applying force to something to lift it, it's getting higher. So that's how it's changing the energy. Now work can simply be calculated by, again, force times distance. So work equals force times distance. This one is really straightforward. It's not hard at all. It's just a little different way to think. Now our example here, how much work was done to a car if 200 newtons of force were applied to push it up a hill that was 20 meters long? So it's just force times distance. 200 newtons times 20 meters gives us 4,000 joules of energy. So we did 4,000 joules of energy to push this car up this hill. That means the car gained 2,000 joules of energy. We lost 2,000 joules of energy. That's what work means. When I did work to push the car up the hill, I was losing energy, the car was gaining energy. Now, very important law we have to remember with any of this is the conservation of energy. Energy cannot be created or destroyed. It can be only converted or transferred. So we can convert it from one type of energy to another. That's how our bodies work. We intake chemical energy, that's when we eat food, and then we're able to move around to think and all that stuff. When we're moving, it's mechanical energy. It can turn into gravitational energy, elastic energy, even kinetic energy because we're constantly moving around. We get that energy from the chemical energy stored in food. Or it can be transferred. For example, if I grab a ball and I throw the ball, I'm transferring the energy from my body into the ball. That's where we do work. So we convert it from one type of energy to another, or we can transfer it by doing work to something. Now, we remember friction. It's the force opposed to all motion. Now, friction does not destroy energy, it converts it to heat, usually. So basically, anytime you have an application of friction to something, it's going to get hotter because it's taking away energy from the movement or kinetic energy and turning it into heat energy. So instead of having the big object moving, we're causing all the little particles that make it up to start moving around. So you're going to have to kind of use your understanding of conservation of energy, work, potential, and kinetic energy tomorrow when we actually get into this. And do not forget, you will have a video quiz on the concepts here and then before we start practice. And if you have any questions at all, make sure you ask them at the beginning of class. See you guys in the morning.